Good morning, everyone. We have Faisal Haque here. He's the founder and CEO of Imparé. Faisal, welcome. If you could please introduce the topic.
Thank you, Rahil. Today we will be talking about verification challenges for AI hardware.
Great. And the audience would love to learn about your background and experience as well.
Okay. I started off at Intel working on processors and datacom engines and cache subsystems and moved through various startups and companies. And then we started a company called Growth Networks, which eventually got sold to Cisco. Um, in 2001, we launched The Art of Verification Vera, which is one of the two classics on verification. Consider two classic books on verification. 2003, IEEE was launched. Accelera launched System Verilog, which is a new language for chip design. And I was the chair of the System Verilog Assertion Subcommittee. In 2006, we published The Art of Verification with System Verilog Assertions. To this day, I think of it as a golden reference on SVA. In 2012, I I was at Qualcomm, and we led the development of the Qualcomm's first handset LTE modem, excuse me, which was used in the Apple iPhone. Then in 2022, we launched Impare.
That's amazing. So, if you could please explain the function characteristic of an AI system, that would be great.
Yeah, so the functions of an AI system really are data processing, model training, model evaluation, and finally inference. The characteristics is it's very data driven, it's multidimensional, heavily relies on matrix operations, and it as a massively parallel architecture.
Right. So, how would you explain the AI hardware system?
So these hardware platforms are designed to facilitate training and deployment of AI models. They typically consist of a neural network, which is a network of basically compute cores. Um, so this figure here shows a kind of a neural network, and this consists of many layers of the network, right? Each layer being a kind of column of compute cores. Um, the compute core is shown here as a hexagon, and that executes arithmetic operations. And within the compute core, the grid array that's shown, and this is a grid of simple PEs, what we call PEs or processing elements, and they typically are optimized for matrix multiplication.
Right. And how would that go to the component level?
Okay. So, it consists of many pieces. As I show here in the figure, there's a bunch of PEs connected in an array. We call this a systolic array, and that is optimized for matrix multiplication and accumulation. Then there's an activation function which can be ReLU or GILU or CILU or sigmoid and tan. You can read the implementation details. Then there is a smart DMA which basically pulls matrix data from memory and loads it to systolic array for calculation. We have different types of interconnects, UCI, which connects the compute core with chiplet with the HBM. There's also Ultra Ethernet, which basically is used as a network or interconnect for the compute core. And of course, we have these processor cores, which are used to control and configure the compute core.
Right. And what would be the verification challenges?
Yeah, many. I typically try to categorize them into four main ones. And these are not the only ones, but these are the ones I think I consider the major ones. There's the scale and complexity. Modern AI chips are have thousands of processing elements. Like we showed in one systolic array, one compute core could be as small as 3 by 3 processing elements, nine, or could be as big as 128 by 128. That's thousands of processing elements. And just the sheer number of, sub blocks like DMA engines, memory controllers, interconnects, that just adds to the complexity. So this could lead to, you can't exhaustively cover this. You have to rely on, so that leads to maybe potential holes in coverage. Then there is massive parallelism. All these AI operations, because the performance, execute thousands of operations in parallel. Um, so correctness can requires very sophisticated models across parallelism, and these things, because parallel operation can introduce race conditions. Finally, non-deterministic nature. Inference is very probabilistic due to the approximations of the number they use. Very we'll talk about it in more detail. Uh, so that requires, that means your traditional scoreboard based approaches may not work, and numerical precision is also an issue because they use reduced form precision formats. So, you have accuracy degradation, and that complicates modeling.
Right. And how does what happens to complexity once we scale up?
Okay, so way to address complexity. One of the main ways, and this is actually pretty typical in verification, is divide and conquer. This is not just applicable to AI chips, but to any complex SoC, but it's especially applicable to AI chips. Um, you break it down, divide it into basic independently verifiable blocks, and apply formal verification wherever applicable to critical blocks. And then, for some blocks that are too big for formal or the full compute core, you'll use a constrained random environment to test that. So for example, systolic array, you can use a constrained random environment or formal. For DMA, you can use formal. For memory controllers, you could use formal. For UCIe, um, the digital part, you could use formal, or simulation. Ultra Ethernet probably better suited for simulation, but I think formal can be applied if done by somebody who understands formal well. And interconnects, of course, are very well suited to formal.
Right. And how would you address some of the challenges for systolic array?
A systolic array is one of the main components, main foundation of an AI engine. So there are two ways, like I said, you can use simulation or C2RTL equivalents using formal tools. If you're using constrained random, you'll build a UVM test bench. One of the things that you need there, and very, very important, is how to generate matrices. So Impare has a very useful tool there that we make available called Weaver. This is a matrix generator. It basically can generate matrices of different sizes and formats. It can do integer, different numbers, number format, integer, FP32, FP16, and it'll help target corner cases. It's fully implemented in system Verilog and UVM, so it's very easy to integrate into a test bench. If you choose to go the C to RTL equivalence route, then you have to build C model to represent the PE, that's the processing element, and then build an array of those to model the systolic array. Um, if you just chose, first thing you would do is build a PE model and use C2RTL for a single PE, and that'll give you full bit exact equivalence and very easy to close. Then you could do a because if you're 128, that will be hard to close because state space issues. So typically, what you do is you take a 2 by 2 or 3 by 3 tile and use C2RTL for that, and then use regularity principle to apply to the entire array. What the regularity principle says, in a regular structure, if a small subset works, then the rest of the structure works the same. Um, and I think that can help you verify the full systolic array.
That's great. How to address parallelism?
Yeah, parallelism, when an AI accelerator is executing thousands of operations concurrently, You can run into ordering issues because order of operation may be affected, and floating point rounding is affected by this order of operations, introduces rounding errors, and then makes it difficult to reproduce and debug, right? Because you may see the error at one time, and then if a different order comes in, you may not see the error. So what we one recommend is you use a seed-based random environment for reproducibility. Then you use formal concurrency checks to make sure your ordering properties are proven and you understand the ordering in on the smaller subblocks. So then you can once you know that, then you can apply those properties at the random environment.
How to address the non-deterministic nature of these AI models?
So in non-deterministic, again, in like I said, is introduced by massive parallelism and rounding errors. What this does is makes inference very probabilistic. So what happens is same input can lead to a variation in the output. So what that means is when you're checking in verification, typically you have a model and you compare the output of the RTL against the model and they should match exactly. That exact match is not possible under these conditions. So what we shift to is statistical variation, which is tolerance aware. And tolerance can be defined in terms of probabilistic bounds or distribution equivalence. That means a value can be within a range, right? Or can have a probability of having a value like X value be 10% and a Y value be 90%, something like that. So that helps you kind of deal with the non-deterministic nature.
Right, and how to address the numerical precision?
Yeah, that's a very complex question. So AI hardware typically tends to use very reduced precision formats in order to maximize the throughput. So when you use low precision math, that introduces a bounded but non-uniform error propagation, which is very hard to model. And then on top of that, floating point non-associativity. If you have typical, integer math, an add operation, the order of whether a plus b or b plus a, you'll get the same result. In floating point, non-associativity means the order of the operand matters. So a plus b a plus b plus c may not generate the same thing as a plus c plus b. Um, so you have to, what this does is this means that you have to be able to predict the order. And as we said in earlier, ordering varies, right? Due to massive parallelism. So that creates complications. So what you have to do is again replace exact equality checks with tolerance-based comparisons. And the tolerance is defined in terms of ULP, exacts for units in last place. It's a metric um, that say defines your operation error budget. So typically IEEE says, you should have 0.5 ULP accuracy for basic floating point operations. So, and then you can use your C++ or C reference models using MPFR library. MPFR is an open source C library that performs floating point arithmetic to a very specified precision. So you can get actual, if you say FP8 or FP16 or FP32, it will do that and it'll give you correct, very guaranteed correct error rounding. So you get the exact rounding that you require for that format. And so you build a model using that MPFR based model, and then you compare the outputs um, using a C2 RTL flow or in scoreboard can use that to compare against against the RTL.
How would you summarize your insights with us?
Yeah, so AI systems, like I mentioned, have a lot of challenges and very complex challenges. So scale and complexity being one, and those we address through a traditional divide and conquer approach. Massive parallelism, you want to have reproducible environments. You can use formal to constrain the ordering, and and that way that helps you into the predicting the output. Numerical precision, you use a ULP based budget for errors, and then use MPFR based models to get your golden outputs. And then non-deterministic nature, replace exact quality with tolerance-based comparisons using ULPs. Uh, then validate within the ULP bounds rather than bit equality. And then also use statistical distribution tests to verify outputs.
That's amazing. Faisal, thank you for sharing your wisdom with us. How can someone contact you?
Yeah, so I first link there is my LinkedIn page. You can contact me at LinkedIn. If you need to get more details, you can contact Mustafa. We have a whole AI toolkit, and if you want to get more details on the Weaver, Mustafa can provide you those. Um, Finally, our website is a good resource for any. We also have an AI white paper that you can reference and that give you some good background on AI. So I think all three of those are available.
These insights are extremely valuable and helpful. Thank you, Faisal, for joining us today.
Thank you, Rahil.
Thank you, everyone.
Goodbye.